So here we have for this semester, the third lectures on the literatures on math science and history, organized by CMSA in Harvard and also jointly with YMSC in Tsinghua University. So today we are very glad to have Harry Shum, Tsinghua professor, used to be in Microsoft, the vice CEO, and he had foreign associate of American National Academy of Engineer, and also with the Royal Society. So he clearly is expert on artificial intelligence because he has trained more than a few thousand people in that subject. And we are very happy to have him to talk about the subject now. So his title is From Deep Learning to Deep Understanding. So Harry.
Well, thank you very much, Professor Yao. And let me first of all share the screen and see if it works. Let me know if you see my screen.
Yeah, you can see it.
Looks good.
Okay, fantastic. Thank you very much, Professor Yao, for inviting me, and thanks, Ryan, for all the support. As Professor Yao said, and the title of my talk is From Deep Learning to Deep Understanding. When Professor Yao asked me to give a talk about what's going on in the field of AI in general, it was really difficult task for me, and it's hard for me to know the level of interest, in this very broad field, in this topic, because AI now is really a hot buzzword. I actually used to make a very bad joke about AI. I used to say that everyone is excited about AI nowadays, especially every company executive is very excited about AI because they're really afraid that people think they don't understand AI, because the opposite of artificial intelligence is natural stupidity. So you just have to know something about AI, but the truth is that the whole field is now overhyped, and but there are some really great progresses there, especially in the last 10 years. So I'm going to use the first probably 15-20 minutes to describe about the latest progress in the field of deep learning in the last 10 years. And then I'm going to point out some problems, issues with the current status of deep learning. Then I'm going to very briefly explain two projects that I'm personally involved and are personally interested, and hopefully to convince you that it is a very exciting area. It's time to really move to deep understanding from deep learning. Let me start by giving you a little bit of history about DNN. Really, this is probably a seminal paper in November 2012 from IEEE Signal Processing magazine. It's called the Deep Neural Nets for Acoustic Modeling in Speech Recognition. It's led by Jeff Hinton, as many of you know, who is one of the three deep learning people who got the Turing Award a year ago. But not too many people knew that Jeff actually did this very important work, really showing the effectiveness of DNN in speech recognition when he did his sabbatical with Dr. Li Deng in Microsoft Research in Redmond. Later on, they showed that DNN really works, and for speech recognition, of course, many other speech groups around the time followed the same direction, and they got very nice work. So they actually put together this very nice paper. It's really very influential. And of course, soon after that, computer vision people followed, and I will show some great examples soon. And most recently, in the last few years, really NLP people and got super excited about the deep learning and deep neural nets, and showing amazing progress there as well. So if I may summarize that, what really happens in the last 10 years in deep learning, I would say the huge progress, the great progress of AI in the last decade, really due to the unreasonable effectiveness of big data. It's because that there's this huge amount of data that we can actually leverage, we can learn from. And also thanks to unreasonable demand and the supply, I would say, for computing power. It's really amazing that how much computing power we today use to really do those deep learning, to solve those deep learning problems. And again, I'm going to show you some examples there very soon. However, I would also say, despite the incredible progress in DNN, we see this unreasonable procrastination towards general intelligence. In plain English, I would say we're not really making much progress in terms of understanding, in terms of general intelligence, despite this amazing, amazing progress in speech, vision, most recently in natural language. So let me just deep dive in a little bit, what I mean by those 3 points. First of all, it's really about how much data are we talking about today in designing DNN systems. I will use 2 parameters to explain to you. One is really the number of layers used in computer vision in the deep neural nets. The other is actually the number of parameters that we use for natural language processing. Hopefully you will be convinced that it's just a huge amount of data that we need to really do deep neural nets. This is a slide I actually took from my student Jian San, who is the co-inventor of ResNet. This is probably one of the most famous deep neural net architectures, if not the most famous in computer vision, that they actually developed in Microsoft Research Asia in Beijing, China. They published the first in arXiv in 2015, and later on they published the seminal paper in CVPR 2016. So as I mentioned to you, that Hinton and others demonstrate the effectiveness of deep neural net initially in speech recognition. And very soon, and they demonstrate that you can apply DNN to computer vision problems. They worked on the this standard data set is called ImageNet in 2012. Just showed, just blew all the previous state-of-the-art and the SOTA results away by a large margin. In 2012, they showed that the error rates really reduced to 16.4%, and when they applied, it's eight layers of deep neural nets. This is stunning because the best results other people could have accomplished only a year ago was like 25.8% of error rates. This is just unthinkable. And of course, it didn't stop there. And then next year, some other group actually showed that you can, even if you just use 8 layers, but if you design more cleverly, you actually can reduce error rate to 11.7%. And the race started from there in 2014, and this new VGG system used the 19 layers, and they got the error rate to 7.3%. And the same year, GoogleNet came out, and they used the 22 layers, and they got 6.7%. Then my students in the Microsoft Research worked on this. They designed this amazing, stunning, the big neural nets, with 152 layers, and achieved 3.5% of error rate for the top 5 error. Just so for those of you who do not work in computer vision, 3.5% error rate is just stunning. It's really way better than any human being can usually accomplish. And some graduate student in Stanford actually tried that, manually look at the error rate. It's actually way more than 3.5%. In any case, it's just to show that when you can design and execute this huge neural net, with let's just say 152 layers, and you get this amazing result. They actually designed in 2015, 2016, the researchers in Microsoft Research Asia, they actually designed even bigger neural nets. They actually stopped at the 1001 layers. They effectively at that time ran out of memory, and but they showed that. So this is a great example that in computer vision, for ImageNet classification task, and the deep neural nets, specifically ResNet with 152 layers, accomplished this amazing feat. Basically, the recognition was better than any human being. On the other hand, the last few years, we have observed a very similar trend in natural language processing. It happened rather quickly. In 2018, this incredible system came out, pre-trained model called the Elmo came out. At that time, Elmo system actually used only 94 million parameters. This really, Elmo really started this new trend of so-called pre-trained models for NLP. And very quickly, BERT system came out from Google. They used 340 million parameters. And then GPT-2 came out from OpenAI with 1.5 billion parameters. We're talking about a billion. So this is already an amazingly big number. In Microsoft, we trained the system called Turing NLG, which had 17 billion parameters. But just a few months ago, GPT-3 came out with 175 billion parameters. And a few weeks after that, Google came out with the G-Shard system with 600 billion parameters. And you can see the race goes on, and the models become bigger and bigger, but the performance continues to improve. And that's just the new reality we are facing right now. It of course comes with huge consequences. And the first of all is really the computing. The computing requirements for doing this kind of modeling, training this kind of models is just stunning. And over the years, we have observed this shift in the entire computing industry in terms of this specialized computing for AI. If you look at that, the biggest winner in this new AI wave, I must say, is NVIDIA. In fact, just thinking about that, for someone like me who has been in this industry for 25, 30 years, it's unthinkable to think about that, another chip company is bypassing Intel to have the biggest market cap. But that's what the NVIDIA did. You just have to tip your hats to Jensen Huang, the CEO of NVIDIA, for recognizing this trend, for just ruthlessly executing his product roadmap. It's just a really amazing story that what NVIDIA has done for this general purpose, from the general purpose graphic processing unit, the GPU, to this AI processing unit, also using GPU. Of course, other companies also tried to match this trend as well. Especially noticeably is Google. With the TPU, they actually also doing an amazing job. But the NVIDIA, wins in terms of offering all this kind of general purpose chips to the entire industry. So anyone in Harvard or MIT and in Microsoft can leverage that. So that's really pretty incredible. And of course, the whole trend continues to move. And initially we have those GPU cloud, and we'll go to the GPU boxes, and you can package all those computing in a small box. Then you see why even those small boxes may not be enough. Then you actually start to even have the GPU clouds and the TPU clouds as well. that's where we are today. And there's a reason that, Jensen is laughing all the way to the bank, and because they are really making huge amount of money, and with the proposed acquisition of AMD, I think NVIDIA will continue to enjoy this leadership position for foreseeable future, in my personal opinion. Of course, all this kind of computing, comes with some cost. There's this really nice paper just coming out, I guess 2 months ago, only 2 months ago, with this very nice table. If you are interested in computational limits of deep learning, and I strongly encourage you to take a look at this paper listed here. It was published July 10th this year by Thompson and others. There are a couple of things interesting in their paper. One is actually they calculated that in the basically, even with the most conservative estimates, in order to achieve 5% of a target for ImageNet, we still are 10 power 5 computing demands away, even accomplish only 5% of the target for ImageNet in general. So that's just the reality we're facing. It means that we still need, if we follow the current computing paradigm, that is, and we still really need more and more computing power to get there. The other thing is really comparing the cost that from, let's just say, the original BERT training, where you have tens of millions of parameters. Now with the GPT-3, you have 175 billion parameters you have to train. So to train a BERT model, it's estimated that you probably need to spend $7,000 to train a BERT model, $7,000. On the other hand, if you want to train the GPT-3 model, it actually requires $1.2 million to train a GPT-3 model. That certainly is a problem for most of the researchers. And I know Harvard is a rich university. Some faculties may be able to fund this effort, but most of the faculties probably couldn't. This is why recently a bunch of faculties, across many universities, top universities, have proposed that we need to establish a national AI research cloud to provide enough computing power that university researchers can leverage. Otherwise, in the near future, all those interesting things, in AI research probably can only be done in a few top companies where they can spend the big bucks. So those are the two points I made, in terms of data and the compute. The third point is that even so, deep learning has shown amazing results. Probably we really haven't really reached to the point of general intelligence yet. And in a way, we probably are still at the stage of lacking of intelligence despite the DNN. We have to go back to look at that. What did we really learn? And why is it so difficult to explain? What we have learned, and have we really thought through about the traditional AI? The good questions in traditional AI, like knowledge representation, cognitive models, or the reasoning. So let me just to show you a really interesting example. Probably one of my favorite examples, in terms of explainable AI in recent years. It's a very nice work, done by Marco Ribeiro, a former colleague of mine at Microsoft Research in Redmond. He actually did this beautiful work, in his PhD thesis from University of Washington. So I'm not going to get into the details, how he actually worked on this thing called explainable AI, especially with his own model called a LIME, or locally interpretable model agnostic explanation. And if you're interested in it, you can actually find this paper online. Long story short, Now, what he did is that he actually used this Google Net to train a classifier to distinguish, if anything in the picture is a wolf or husky. If you look at this picture here, this is a slide here, you see 6 pictures here. And there's a classifier, so the machine learning system did a great job, in general, because it actually predicted 5 out of 6 results right. There's only 1, and he got it wrong. And so it's in general, it's actually not really too bad. The question is that, why did they get this thing wrong, or even why did they get others right? So of course, you have to be careful when you predict a wolf versus a husky. And if you predict something is a husky, then you bring home and it turns out to be wolf, then you are in trouble. So eventually what he did is actually using something called the related pixels, which pixels actually are used in the DNN to really identify whether this is a wolf or this is husky. And if you look at that, for all those 6 examples, those pixels actually identified, for the first one, for example, are those pixels here. And it says, because of those pixels, then they say it's actually a wolf. Because of these pixels, then they'll say it's a husky. Then because of these pixels, then we'll say it's a wolf. Now, if you look at that, with human eyes, you probably would agree with me that, from those pixels on the right-hand side, none of those things really are saying anything about the particular object, whether it's wolf or it's husky. It's really looking at the background pixels that if it feels that it has snow, if you have snow on the ground, then it says it's actually wolf. If you don't, if it says it's husky. It's just as simple as that. So this is really stunning to realize that, with all those amazing deep neural nets, what we have trained from the labeled data, it actually trained on some spurious statistics. And so this is very nice work by Marco Ribeiro, and it really shows the limits of so-called deep learning. So with this kind of result, you probably agree with me that it is really not that much much intelligence there. It trained and it got reasonable results, but not exactly about this particular object, wolf or husky. So similarly, we can also remark on the natural language side, especially, GPT and the BERT. And there has been some hot debate recently on whether this gigantic natural language models, actually learned, for example, that although BERT-based models, achieve, SOTA results, state-of-the-art results on many NLP, benchmarks. Recently, there's a paper from Facebook AI argued that BERT exploits spurious statistics patterns, just like what we have seen in that wolf versus husky, where really the snow pixels made all the difference. Similarly, NL, it says that the BERT model really exploits this kind of statistical patterns, the data set, instead of really learning the meanings in the generalizable way, like what the humans we do as we learn language, natural language. So that's the thing, what's really going on. I should also say that for those of you who are not very familiar with natural language, pre-trained models, well, right now the pre-trained models are the hottest things, and there are generally 2 kinds of pre-trained models there. One is in terms of language understanding, that's mostly represented by BERT-like models. Then there's our language generation that's represented by GPT type of models. And all these kind of models are actually vulnerable to adversarial attacks. So I'm going to show you a couple of examples in the next slide. So there are really 2 fun examples here I'm showing you. And let me start with the first one on the left-hand side. if you look at this one in the left-hand side, and we use the BERT-like model to really identify, say, well, if you have this article about the Super Bowl 50, and say Peyton Manning became the first quarterback, blah, 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 and so let's just say that without the last line of blue, the last blue line, then you ask the question that, what is the name of the quarterback who was 38 in Super Bowl, 33? And the system actually doing pretty well. It says it's actually John Elway. So that is correct. But if you do this adversarial attack by adding something stupid in the end, just to confuse your system, then you say quarterback Jeff Dean had the jersey number 37 in Champ Bowl, 34, and it's just a completely joke. And then the system actually, will give this prediction, and the adversary, it says Jeff Dean, which is totally wrong. So now you see, the whole system is really not very reliable. And the right-hand side is also another very interesting system called the text fuller. And it's actually detecting, whether the sentiment is negative or positive. The left-hand side, it actually did it right. You just say the characters, casting impossibly contrived situations are totally estranged from reality. So the sentiment there is negative. But if you carefully switch out a couple of words, without changing the real meaning, and the text fuller, shows that, you just got fooled. And then the sentiment is actually positive. So we did that kind of experiment, and they showed that, with this kind of BERT results, generally the results are actually pretty good. It's actually the accuracy is in the high 80s or even 90s. But if you put this kind of adversarial attack, and the result just completely plummeted, and this is just horrible and not usable anymore. GPT-2, on the other hand, the previous one I showed you is actually in BERT, is actually language generation in the modeling. Then if you look at the GPT-2 results, by the way, for those of you who are interested in natural language, recently, the huge buzz about the GPT-3 who recently came out, from OpenAI, especially with the collaboration partnership with Microsoft. It shows very interesting results. Even before GPT-3, and right now GPT-3 is still not very accessible for everyone, but the GPT-2 was accessible for a lot of people. People did a lot of interesting experiments. I'm just showing you some results here. You look at the GPT-2 results, they actually sometimes very reasonable. Let's just say the first result shows that two soldiers walked into a bar. Then, you can fill in the next half of the sentence. It says, well, two soldiers walked into a bar. Then GPT-2 will say, well, in Mosul, and spend all of their money on drinks. So that's plausible. It's actually pretty good. On the other hand, then you say, well, another example says, yesterday I dropped my clothes off at the dry cleaners and I have yet to pick them up. Then say, where are my clothes? And the answer is actually at my mom's house. It's completely ridiculous. And similarly, the next example also shows it's really not working. So the trouble of GPT-2 as a solution, that of course is actually pretty obvious, right? Because all this kind of natural language deep learning models, they are just they're just models of word usage, not really models of ideas, because a model of word usage, is just being used as approximation, right? It's approximation to a model of real ideas, and so that's the thing. So the word usage is not reliable. It's the approximation and not reliable, approximation to knowledge. It's not a substitute for knowledge itself. And so big doesn't mean, even so you have 175 billion parameters in GPT-3, you will see very similar mistakes being made. It shows that in the big models doesn't mean in the robust models. For those of you who are interested in AI and the general intelligence, I highly recommend you this very interesting book by Gary Marcus and Ernest Davis. It's called the Rebooting AI. Actually, Gary also wrote the very nice long paper published on Archive called The Next Decade of AI, which I also highly recommend. Basically, he challenged the deep learning on a number of things, and they also suggested a few directions that we could do. So if I go back to what I said a little earlier about what really happened in the previous decades, last 10 years, the unreasonable effectiveness of big data, thanks to unreasonable supply and the demand of computing power. Yet, we see this unreasonable, slow progress of general intelligence because in deep learning, very often work like magic, but only to approximation. So, like Gary, I would argue that time is now to really move to deep understanding from deep learning, and sometimes people would call this robust AI. So again, I share some of Gary's arguments about narrow AI versus robust AI. When we say deep understanding or robust AI, we really need to count on those AI systems to apply to a wide range of problems, a systematic and a reliable way. We should be able to synthesize knowledge from a variety of sources such that we can reason flexibly and dynamically about the world, and we can transfer what we learned in one context to another. However, it's very easy to say, and because people in some way have been saying that in general AI over many decades. The question that what can we really do? What are the research directions that we could possibly pursue? Especially, I would say, in near term. I certainly believe that there are some amazing opportunities near term towards understanding. For example, that the result of ML, machine learning, should not be just a set of classifiers, one for each task, but a robust AI agent that continues to learn skills, knowledge, by practicing and by exploring. So in the rest of my talk, I go a little bit deeper on two research directions I like, and they are also published very recently in the last few months. The first one is really going back to rethink about the objective of machine learning. What's probably going wrong with many of us in the last 10 plus years? What exactly are we learning here? Why do we just jump almost blindly into deep learning without thinking about what we exactly are trying to learn or trying to optimize? The second one is really on the natural language processing side. That is, I'm going to use an example of task-oriented dialogue to show you that hybrid modeling, hybrid neural and symbolic modeling is probably a good way to go to make AI more robust. So the rest of the talk, I get into enough details, and if you are interested, you are very welcome to read those papers cited in my talk, and to really get into details. Both of those projects are very, very new, and as I said, published only in the last few months. The first one is a very nice piece of work by Professor Yi Ma at the University of California, Berkeley. The paper is called Learning Diverse and Discriminative Representations via the principle of maximal coding rate reduction. It's published in Archive and is submitted to some conference, and hopefully will be accepted soon. It's really about the rethinking about the what and how we learn. The paper, the idea there is, in short, is called MCR2, maximal coding rate reduction. It's about the representation learning between classes, within classes, and also maximally diverse. this is actually some very interesting guiding principle there, like what Aristotle said, that the whole is actually greater than the sum of parts, and in a way that Yima is saying the whole is actually to be maximally greater than the sum of parts. You will see, why we say that in the next few slides. And there's a key idea there is really how to. It's actually about learning to compress and compress to learn. So let me show you some picture here to just explain to you what we are really talking about. So in learning, in a way, by and large, we are talking about is really, we have some very complex, high dimensional data, and we try to learn and to represent with some kind of low dimensional structures. Example, we are seeing here is that, there are a bunch of this, you have this point clouds, and to help you to understand better, we color coded that there are really three classes here, 2 lines and one plane, coded in blue, green, and black. And sometimes, they just perfect, like in the figure A here, and you have all those sample points, perfectly sampled from those 3 representations, 2 lines and the plane. But in practice, you often see have some noises, and like in B, you see some noise. And in practice, you also see some kind of outliers, which is even more annoying. And in this case, in figure C, you have those red points, showing that, that's the thing. So there are really 3 related but different objectives of learning that we're trying to do. The one is called interpolation. That is to identify, which samples belong to the same structure. And the 2 is extrapolation. That is to determine to which structure a new sample belongs to. Then you also have the most interesting thing is called interpretation. That is find the most discriminative and compact representations for all those data points. So in deep learning, and both fortunately and unfortunately, the learning is lumped into a black box. So we're trying to do this classification that in all the high dimensional data X, which lie on a mixture of low dimensional manifolds. Then you have this Y, so the X is the data, then you have Y is the class label of X represented as one hot vector. The goal is really to learn a nonlinear mapping, F, from X to Y. Then in a supervised setting, what you do is you basically have the labels. And the mathematical, that's what this deep neural net is trying to solve. Typically we use the cross-entropy loss. And you can do that, but you can immediately observe some characteristics about this kind of work. First of all is that, a big deep neural net can fit any labels, even if it's a random label, give me enough parameters that I can fit in something. However, the statistical and the geometrical meaning of those, of this model is just not clear, and more specifically of these internal parameters or features, just not very clear. And of course, because of this kind of representation, it's really highly task dependent and not robust. So in a way that we need to go back to ask that, what do we really learn, from doing this kind of fitting, right? In terms of interpolation, extrapolation, or interpretation of the data. So there's one particular line of work that I like, from this Berkeley crowd. It's actually called generalized PCA for high dimensional data with a mixed low dimensional structure. The idea there is really about learn to compress and the compress to learn. It's really about how you represent the mixed data, and it's all about seeking a good representation, and that actually helps this learning. So there are really probably three aspects or elements in this kind of ambitious representation of data. Instead of really this mapping x to y, you try to really come up with this good representation or intermediate representation or whatever you call it. It's called z. You try to find this new representation of f from x to z, such that you go from the nonlinear structure in x to linear structure in z, and you go from separable x to maximally discriminative z. By that I mean those z-axis should really try to be perpendicular. And then you also go from a non-parametric, which is just the sample points, to mostly compact, or you have a structure. So that's really what we're trying to do here. And again, the objective function can be elaborated even more with more details here in three aspects. The first one is really between class discriminative, and all the features of samples from different classes it should be highly correlated, belong to different low dimensional linear space. And then the second thing is really within the class compressible, and all those features of samples from the same cluster and they should be relatively correlated, right? And the third one is really so-called maximally diverse representation. That means that the dimension of features for each cluster should be as large as possible, as long as they stay uncorrelated. Just try to expand more space. So that's basically what we're trying to do, to seek this optimal representation, using compression techniques. So then I get into a little bit more detailed mathematics here, and so that's how Ima and his students actually formulated. So they try to maximize the difference between the coding rates of all features and the average rates of the features with respect to their classes. So the first term here is R, that is really expand overall Z as big as possible. And the second term is the sum of all the subclasses, all those classes, and you try to compress each class representation such that they can be as small as possible. Then, the delta, the coding rate reduction, can be really, maximized. In a way, what we're saying is that, that this similarity repel and the similarities attract. Then we can go into a little bit more details here. Write down the equation, and this is just an easier way to write this thing down. And you can see from this equation, it becomes very clear what we mean by maximize the coding rate reduction, MCR square. So for those of you who are interested, please read, Yi's paper on arXiv. So after, the paper was written, the authors actually tried to explain, what's really going on, using a sphere packing and the counting as an example here. So basically, what they are saying is that suppose you have this thing you try to represent, try to learn. It's kind of like you try to find a space where you can pack the most spheres. If you actually can actually have those two axes perpendicular, then you can really expand the space in like a full circle here, where you can really pack more balls. In this case, all those blue balls you can pack over there is way more than the right-hand side if you actually have two axes to form an ellipse over here. So basically, the rate reduction gain delta R is all those spheres. That is how big your space Z really is, and subtract those two lines for each class. you know, how compact you can put it there, you know, basically try to minimize the number of bars to represent those two lines. And in this particular case, is the number of green bars in those two axes remain the same. So you've essentially, you just counted the blue bars, you know, you can go count it. In this case, it's more like 120 versus 72. So hopefully you get this idea, you know, what's really going on. And the interesting thing is that, you know, for those of you who work in math and in Professor Yao's Math Center, you know this line of work way more than I do. We just recently observed, you know, noticed that there's some very interesting work, you know, on 8-dimensional sphere packing by Marina Wiazowska in 2017. And I have to admit that I didn't read that paper very carefully and to really truly understand, but the you know, in spirit, it's very related to this line of thinking, and for this particular line of work, that what we are truly learning. So that's the one line of work, you know, I want to just give you a taste of it. And for those of you who are interested, and please refer to that paper. Yeah, I know I'm moving on very, very fast, but I do want to quickly move to the next topic. And hopefully with this simple explanation, I get you very excited about, you know, the idea of learn to compress and the compress to learn. There's this very nice math principle there, the clustering, the via compression, classification via compression, representation via compression, and expression. So that's the thing. It's pretty exciting work. The second line of work I want to explain to you is something that, you know, I got more involved with my colleagues in Microsoft Research in Redmond. So along the line of natural language processing, in particular, we show that, you know, this hybrid model, hybrid neurosymbolic model, is a great way to go, at least to get us closer to more robust AI. This paper is also published about 3 months ago. It's something that's about a system that they built in Redmond called the Soloist. It's about building taskbars at scale using pre-trained natural language model, but not like GPT. It's actually called a GTG, which means grounded text generation, and generator, which I may explain to you soon, and also using a conversational learner to really fine-tune the final results. Overall, the system goes you know, a few steps. You know, one is end-to-end neural model with symbolic constraint. Two is actually grounded text generation. Third is actually followed by few-shot learning. So that's really what's going on here. For those of you who are not familiar with natural language dialogue modeling and the dialogue session, and let me show you an example here. So I'm not going to walk you through, you know, line by line, but let me just explain to you that the more and more natural language dialogue systems have been developed in the world in real applications, and like a customer support and or any kind of service industry where you actually need to answer phone calls or web queries about it. People might have questions. So this example shows that you know, you can switch the context, that initially the user is looking for a museum in the center of town. Once the AI system answered about the museum, then the user switch gears and, well, how about in the same area? I actually would like to get a restaurant. And oh, by the way, can you actually book the restaurant for me? So that's the short description about, you know, this multi-domain dialogue session. And so most task-oriented bots dialogue systems are implemented using a modular system, you know, consisting, first of all, you have NLU, which is natural language understanding, to detect the user intent. Then you have this state tracker to keep track of dialogue states. Then you have a policy to select the next gen actions, next agent actions, and then an NLG to convert an action into an NL response. So recently, there has been a trend in building a non-modular system that used a neural language model to replace all the components, all those 4 components, in the up, the picture there. So we can directly generate a response based on user input. In a way, it's kind of like a black box. So the system is widely used for social chatbots in research community, where you probably people tend to be more tolerant on the nonsense results. However, even so, in those cases, you can generate fluent results, and the results are just not really grounded or just incorrect. So if you take a look at that, and here is actually a dialogue between a human user and the neural conversational model from actually Dialog GPT from Microsoft. You can see that this example here actually is pretty fluent, and if you just walk through this thing, and this thing is just really amazing that the AI can really converse with the human pretty well. On the other hand, if you have a more the task-oriented example on the right-hand side, so it's just not right. You just don't really get it, and then the AI just doesn't really get it. So that's basically the problem we face if we want to do this kind of task-oriented dialogue. This is what I want to explain to you about this system. I'm showing you an example here, really get you understand what I mean by response, generate the response with and without the grounding. On the left-hand side is without the grounding, and it's just not consistent. And then you say, well, where's your hometown? You say, I live in Indonesia. Then where are you from? You say, I'm from England. So it's just it's just inconsistent, because the language model just doesn't really have this knowledge or tracks what's really going on during the dialogue. You say, how old are you? You say, I'm 18. So far so good. Then you say, what's your age? It says, I'm 16. So that's just completely wrong. If you have the grounding on the right hand side, then you get it right. So then the question that what can we do, right? This kind of dialogue system. And again, a typical dialogue system, then you have those 4 modules. What you can really do. So you go through those four modules here. So what's really going on is eventually, in order to really build this robust AI system, and you really have to go to the deep understanding side, the understanding side. So what's going on with this dialogue state tracking on the up right-hand side is it's kind of like acts like a cognitive model, with humans, and the outside knowledge thing like a database and APIs and other things, it's kind of acts like the knowledge base. Very often you have symbolic representation. Sometimes you even have common sense encoded. Then you go to the policy side and you have to select the actions. Is kind of like a reasoning. So all those things together, cognitive model, knowledge, and the reasoning is what we typically say about robust AI or deep understanding or traditional AI. So that's what we actually try to do. So with all this kind of context, what we're trying to do is actually we're going to build a hybrid model so that we can re-implement knowledge, reasoning, cognitive model with modern machine learning techniques, especially this end-to-end data-driven approach there. The deep learning for knowledge representation, for dialogue state tracking, and then the reinforcement learning for dialogue policy learning, and finally, even transfer learning, not only with pre-trained models, but we add fine tuning as well. So that's the high level that we believe we have to do to have this kind of hybrid model to do this right. So more specifically, let me get into a little bit more details there, and then also a little bit of mathematics here. Is that this slide really shows that how we formulate this modular dialog system, kind of like an autoregressive model here. So the modular system can be viewed as a data generation pipeline. This consists of those 4 modules I already talked about. This is NLU, DST, policy, and NLG. And the process this data in sequence, right? And the output of a module is the input of the next module. So if we implement each module using a transformer based neural network, and allow all those neural networks to share parameters across the entire pipeline, then the whole pipeline can be implemented using a transformer model, which we call the GTG. By the way, this is called transform model, for those of you who are not familiar. It's really the latest the buzzwords with pre-trained the natural language model. It's very, very popular. So this is really what's really going on, that how we can really solve this. You start with this dialog history, and then you get the first task is about the belief state prediction. Then you take the dialog history and the belief state. Then you have the second task is really about the grounded response generation, and where you also use the database state. And if you're looking for a restaurant, then you have the restaurant data here. If you look for museum, you have the museum data here. And then finally, you take some of those responses and you do contrastive learning, and just to really fine tune, get it right. So that's basically what's going on. And mathematically, you can decompose this complicated probability into a few terms in the multiply. You can work that out. It actually works out pretty well. Specifically, then you really look at that, this is really how we actually do it, right? So the task 1 is a brief state prediction, trained on dialog model belief state pairs. That's what we do. And the task 2 is the grounded response generation, trained on input output pairs. And the input now you have 3 things, and it's a concatenation of dialog history, belief state, and the database state. And the output is actually delexicalized response. The third one, for those of you who are not following the latest, the deep learning, is probably not as familiar. Maybe I explain a little bit more here. So it's something called the contrastive learning. So we view each dialog turn in training data as a positive example, and which consists of 4 matched items. Now we then sample a few negative examples, by replacing one of the items with a randomly sampled item. So negative examples contain mismatched items. Then the whole system, GTG, is learned to give a high score to a positive example and the lower score to the negative example. This is what people call the contrastive learning. So anyway, so with that, we get some really nice results, and then we are able to really compare this an amazing thing called the GPT that you hear from the OpenAI versus what we do here called the GTG. And the GTG actually learns to predict dialog states, and it generates grounded responses for task completion. We pre-train on dialog cops, and we fine-tune to complete the specific dialog tasks. And basically, we learn what to say to really get the job done. Here are a couple of examples here. Let's just say that you already have some dialog history. GPT-2 will give you some garbage results, and because it doesn't really have this notion of grounded text generation. On the other hand, if you look at that, GTG it will be able to generate this delexicalized response. And from the previous history here, just like what we have shown in the previous few slides. And then the final response, you can fit in, like say, hey, I have booked you a Tesla. The contact number is 1234, and anything else I can help you with, right? So that actually responds really well, because previously the human really asked that, I want to leave after 7:15, and he said, well, I would like to get a taxi from University of Cambridge to Pizza Hut. So that's, looks really reasonable. That's what we actually try to do. So we have worked on this thing, on a number of these benchmarks, and I'm probably going to skip the next few slides without getting into a lot of details. And suffice to say, we get amazingly good results, and especially if we compare with the state of art, and there's a huge jump in all those metrics there. So we got very, very excited about this result, and I'm going to skip these few slides, and just trust me that the results are really, really good. We did the human evaluation as well. Again, we just outperform all the state of arts results previously by a large margin. So let me conclude what I have discussed in the last hour, the entire hour. Hopefully that you heard from me that the whole field has made amazing progress in deep learning, especially in speech, vision, and more now in language understanding. However, despite all the progress there, we are not really close to anything, in terms of general intelligence. So time is now, for us to move to really focus on, really do great research, in terms of, understanding. We should move to deep understanding from deep learning. In a way, what we're trying to do is actually, we are working towards a robust AI, so that we can statistically, geometrically, and semantically really explain, what AI is really doing. So I'm going to stop here. And I also want to acknowledge, Dr. Jian Sang of Face++, Professor Yima of UC Berkeley, and Dr. Jianfeng Gao and Dr. Marco Ribeiro of Microsoft Research for their slides and the help for discussing. Thank you very much. And I'm going to stop here, Professor Yao, and let me know if I may have some time for questions and answers. And back to you, Professor Yao.
Right. Are there any questions?
Yeah, Harry, so you can see these, there's a Q&A tab.
Okay, yeah, I see one comment there.
Mike, could you start?
Where can we find the material? I'll be happy to share some of the slides here, and probably people will be very interested in those few papers I referenced. I make sure that I get the link.
Yeah, any materials you can give, we'll post on our website for you.
Yeah, okay.
So my Douglas has a question. So could you?
Okay, yeah, feel free. Yeah, you can use the type, you can ask.
Mike. So Ryan, what happens?
Michael, if you raise your hand, I can unmute you. I just need to find you in the
Mike.
Yeah, I'm gonna allow him to talk.
Unmute. Can you hear me?
Yeah.
Yeah.
Oh, good. Yeah. Okay. That was a great talk. Very clear explanation. Hasn't stated things. So I very much agree that the next step would be to combine some neural and symbolic technique. I have a question about the language models and transformers, which is that on the one hand, certainly I think pretty clear that they don't understand text, anything, anywhere near human level. And on the other hand, it does seem like they do much better than a simple co-occurrence statistics or the previous concepts of describing language. You're using them in your own system. Is there some thought about what is the class of tasks that a transformer language model can do? And a more specific question would be, can it learn grammar? For example, there's a number of groups, but in particular, Chris Manning's group at Stanford is giving very interesting evidence that they do learn grammar. What do you think about these questions?
Yeah, that, Michael, those are good questions. And you also mentioned about Chris Manning's work, and indeed, Chris has been doing amazing work, over a long period of time in overall, in many NL problems. And I haven't seen the latest, work, how they use the GPT type of method or mechanisms to really learn grammar work, and intuitively you should be able to learn something there. My own observation is that really the pre-trained model are really very, very powerful. And again, and I go back to Elmo, being really the first one to lead the way, to demonstrate that pre-trained model really work. Recently, there are really two lines of work over there. One is really on the BERT, and the other one is GPT. BERT is really more about the kind of analysis and the recognition, and the BERT is and the GPT is really more about the synthesis. Most recently, GPT got a lot of buzz and a lot of hype. What's going on. My own view is that I think the synthesis is easier. It's if you look at the GPT kind of stuff, that you can really use that to synthesize something very, very interesting. For example, that even with GPT-2, there's a very nice app called AI Dungeon. If you're interested, you can download that from the App Store. It's someone really clever. He actually used the GPT to generate children's stories. He also injected some very good structure over there. I believe his dad is some famous child story author or something like that. So he got some background over there. If you're actually clear about the genre, just the type of children's story you want to write, and then you start to fit in, automatically generate some text over there, and you can also respond, and you can kind of fill out the things you like, you don't like. So to me, I think that the synthesis work, you can clearly see that the next few years, there will be some very exciting work over there. We also do something like that in this Xiaoai system, we develop in China. We have this thing called the X-Writer, doing very similar things. If you get stuck, you write your term paper, you get stuck that, you can actually ask AI to try to hypothesize some more text for you. So this line of work, I would say, would be probably very, very interesting. And I definitely expect to see more work, along this line.
Thanks. Can I ask, so another in-between task,
yeah.
I think more complicated than pure synthesis and less than actually understanding is reading comprehension, where you give it a text that contains the answers, and then you give it a query where the answer has to be based on that. And then that one also seems more impressive than just a simple language model. For example, LNAI, unified. Do you think transformers should be able to do that, or do you have the same sense that that's too much understanding for the models we have now, or do you have an opinion?
Yeah, I think I do have an opinion there, and as you said that LNAI is doing fantastic job. I believe Elmo is LNAI, UW, those guys came out a few years ago. It's very nice work. The thing is that it really depends on how you compare. What do you really mean by understanding, right? All this kind of simple reading, understanding things. We probably already have systems that is outperform ordinary humans, and it's already there. But it's statistical, sometimes spurious. Sometimes you get it wrong, just ridiculously wrong, and because the transformer is not really trained right, quote unquote. So this is why I actually believe that this hybrid model is the right way to go. Even so, I only showed one example of a task-oriented dialogue. What you refer to, Michael, there could be a great example where we can actually start to add more structures over there. By structure really means some kind of knowledge representation, some kind of cognitive model. I do expect that the significant progress will be made, along this line in the next few years. I really believe this hybrid model is the right way to go. That's why I urged my colleagues, especially Dr. Jianfeng Gao, to write this paper. In a way, rewrite the paper, to make sure that this hybrid approach, we should really highlight this hybrid approach.
Yes, thanks.
Okay, Harry, there are some other questions. Do you see it?
Oh, from Q&A, yeah. Let's see.
The idea of compatibilizing the representation data and using sphere counting.
Oh, there are actually three questions. Let me start with, let me see. Let me answer the second question. This is actually very technical. The answer is no, so it's actually very quick. Is there any analysis about the well-postedness of GTG and so on? The answer is no, not yet. And in fact, we look for smarter students to work on this. If you're interested, please contact me and Professor Yao, and so I connect you with Dr. Gao and those guys. It's a very interesting, it's a good question. So the answer is no. So that's the second one. The first one says, sorry, I'm new to this, so I might be miscommunicating here, but I recall that you spoke about using the idea of compactifying the representation sphere and using sphere counting-based ideas to determine how one should do localized orthogonal things. How did you guys already at a high level? How did you guys algorithmically detect a higher level? Yeah, so it's a good question there. First of all, I think you can read the paper to get the more details there. Secondly, I would say that typically when you do this kind of thing, you usually do two kind of things over there. The one is really supervised, the other one is really unsupervised. And this is how you really try to detect this higher level manifold in the topological structure there. By the way, the EMA actually published two other papers before this one. One is really on the clustering, the other one is actually on classification. Classification in the sense of supervised, and the clustering is in the sense of unsupervised. So that's pretty much what they did. The third question is I have a problem. How to make machine understand the common sense knowledge of a healthy adult? For example, we can point out the people who impress us in photos without much effort, but the current machine learning still need the bounding boxes. Yeah, that's a tough question. How to make the machine understand the common sense knowledge of a healthy adult. Common sense knowledge modeling until now is a very, very difficult problem, and a lot of people talk about that. There's very little progress made over the years. It's just hard to really codify knowledge, common sense knowledge in particular. Over the years, and the probably the biggest effort along this line is what called the CIC, C-Y-C. It was thousands of man years of effort, if I'm not mistaken. It's a very difficult problem space, and yeah, there's no simple answer from me, and my best answer there is that you probably should spend some time and read some literature there. And then the next question is also, is the natural language processing easier in other language? So is this negligible? I think it's very similar. I would say my only experience is mostly Chinese and English. I wouldn't say anything is that particularly easier or more difficult. And although, a lot of people believe that in the Japanese is difficult, in the sense that many translation systems people have tried that, you know, the error rate for Japanese to other languages than the vice versa is typically higher than, let's say, Chinese, German to English. But it's hard to say, you know, it could be just that people haven't really tried hard enough, you know, translating Japanese, and they didn't have enough data. But I would also point out that if you study computer science, almost any other subjects like computer vision and other things, or programming language, there's really no difference, you know, in culture and the languages. NLP is the only area I can think of. If you do computer science, they use something called the Chinese NLP, and that is actually significantly different from English NLP, and you do have to have some background. So that's kind of interesting. So last question I see here is that you mentioned symbolic representations, but you don't use any symbols or logic-based representations like Ernest Davis and Gary Marcus advocated, but the continuous vector representation of knowledge. So you don't mean hybrid using logic. This is a very good question. And probably some minor misunderstanding from your side. So first of all, you know, I admit that, you know, when I say this hybrid representation, hybrid modeling, and the symbolic, I do overgeneralize a little bit here, but we don't really use continuous vector representation. We actually use database. So the knowledge database is what we used in this particular system. So in a way, you know, is this really symbolic enough? And you know, probably is. And we really haven't used a lot of logic here. We haven't really done a lot of reasoning there. So Gary and Ernest, they kind of talked about, you know, the general AI, you know, you have to get multiple things right. As I mentioned earlier about the challenge of common sense modeling, it's just really, really hard. My own view is that, you know, you just have to take advantage or leverage this incredible mechanism called end-to-end neural computing, data-driven, you know, you can do it. They already showed that, you know, GPT is an example, transformers and BERT, you know, they showed that, you know, you throw in enough data, you can do this thing, very interesting. Now I see this opportunity of, you know, adding more structure there, adding more symbolic representation there, and then we'll be able to do things like we have shown this example of grounded text generation. So it's just a good step towards the right direction, in my opinion, and that's why I would like to present this to Professor Yao's class here. Hopefully get more students excited about, you know, get more people work along this direction. And again, you know, any of you, if you are interested in this, please contact me. We'll probably have enough internship slots, you know, for you guys.
Okay, great. I don't see any more questions. So it's getting, well, I mean, close to time. Are there any more questions?
Yes,
okay, thank you very much for the beautiful talk, Harry. So I'm really happy that you gave this talk.
Thank you very much, Professor Yao, for inviting me. Yeah.
Thank you. The next talk actually would also come from Microsoft. That's Michael Freeman, who is going to talk at 12:30 on 4-dimensional point-connect conjecture.
Yeah, Mike's talk will be a lot more interesting, I'm sure.
No. I mean, one is older, one is very new. So that's very good. Okay, thank you, Harry.
Thank you very much. Yeah, appreciate it. Thanks, guys, for listening. Yeah, bye-bye.
Bye-bye.